You're about to go back to sleep when your phone rings. It's your manager. P99 latency has spiked to 10 times baseline. Users are complaining. The application is dying, but your dashboard still shows everything's healthy. This is the moment every engineer dreads. What's really happening? The truth is, your dashboard is lying to you, not because the metrics are wrong, but because you're looking at the wrong things or interpreting them without context. Traditional metrics like CPU percentage, free memory, and disk I/O can be deeply misleading. Today, I'm going to teach you to read between the lines and understand what these numbers actually represent at the kernel level. 3. What you'll master today. By the end of this session, you'll have 5 key capabilities. First, you'll learn to read between the lines of Linux performance metrics. You'll understand not just what the numbers say, but what they mean in terms of actual kernel behavior. Second, you'll identify hidden bottlenecks that basic monitoring tools completely miss, like context switching storms or memory pressure that doesn't show up as low free memory. Third, you'll apply a systematic troubleshooting methodology. No more randomly trying tools and hoping something works. You'll have a process. Fourth, you'll recognize performance patterns from real production scenarios, the signatures of different failure modes that I've seen over thousands of incidents. And finally, you'll know exactly which thresholds matter and when to take action. Not generic advice, but battle-tested numbers from operating at scale. 4. Part 1. CPU Troubleshooting. Let's start with the resource everyone thinks they understand, but actually don't. CPU. We're going far beyond just running top and looking at percentages. We're going to understand the hidden metrics that destroy performance. 5. The load average mystery. First up, load average. This is one of the most misunderstood metrics in Linux. Here's what most people get wrong. They think load average equals CPU utilization. It doesn't. Load average measures the number of processes waiting for CPU plus the number of processes waiting for I/O. That's a critical distinction. So when someone tells me their server has a load average of 8.0 on a 4-core machine, my first question isn't, "That's bad, right?" It's, "What is your application doing?" A database server handling thousands of concurrent queries efficiently might have a load average of 20 on a 4-core machine and be completely healthy. Why? Because all those processes are efficiently waiting for their queries to complete. But a web server with a load average of 2 might be completely saturated if every request is CPU-intensive work. The metric that actually matters is run queue depth. This tells you how many processes are truly waiting for CPU time right now. You can see this with VMstat. Look at the R column. If the run queue consistently exceeds your number of cores, you have CPU saturation. That's the signal to worry about, not load average by itself. The command to remember here is VMstat 110. Watch that R column over time. 6. System versus user CPU time. Now let's talk about a pattern that I see destroy performance all the time when system CPU time exceeds user CPU time. When you look at CPU breakdown, you see 2 main categories. User time is your application, executing its code, the actual work you want done. System time is the kernel working on behalf of your application, handling system calls, context switches, memory management, network stack processing. Here's the red flag: when system time consistently exceeds user time. This means your process is spending more time asking the operating system to do things than actually doing its work. I'll give you a real example. We had a service running at 70% CPU utilization. Sounds reasonable, right? But when we broke it down, we saw 20% user time and 50% system time. Using perftop, we traced this to excessive malloc and free calls. The memory allocator was dominating system time. The fix wasn't adding more CPU, it was implementing object pooling to reduce system call overhead. The command here is perftop-g. This shows you exactly what's consuming kernel time. Once you know what the kernel is spending time on, you can optimize your application to reduce that overhead. When you see system time dominating, your application architecture needs fixing, not your infrastructure. 7. Context switching, the silent killer. Now we get to the silent killer at scale. Here's what happens during a context switch. The kernel saves the current process state, all the CPU registers, program counter, stack pointer, into memory. Then it loads the new process state from memory back into the CPU. This takes about 2 to 4 microseconds. That doesn't sound like much, right? But here's the real cost: cache pollution. When you switch processes, all the data that was in the L1, L2, and L3 CPU caches become useless. The new process has to reload its data from main memory. Cache hits take 1 to 10 nanoseconds. Cache misses take 100 nano or more. That's a 10 to 100 times slowdown on every subsequent operation. At production scale, this is devastating. A server doing 150,000 context switches per second is in serious trouble, even if CPU utilization is only at 70%. Let me give you a real scenario. We had a microservice handling 50,000 requests per second with acceptable latency. Traffic increased to 60,000 requests per second, and suddenly P99 latency exploded 5 times. But CPU was only at 70%. What happened? Context switches jumped from 40,000 per second to 150,000 per second. The thread pool was misconfigured, creating thread thrashing. Each process was getting tiny 1 to 5 millisecond time slices instead of the 100 to 200 milli they needed to do useful work. The production threshold you need to know: above 50,000 context switches per second consistently, you have a problem. Above 100,000, it's severe. The commands are PIDstat-W15 for per process switches and VMstat for system-wide. If you see high numbers, the fix is usually reducing threads, using async I/O, or batching operations. 8. CPU steal time in cloud. If you're running in cloud environments, AWS, GCP, Azure, there's another hidden CPU thief: steal time. Steal time is when the hypervisor divs your CPU cycles to other tenants. You're paying for those cycles, but you're not getting them. Here's the insidious part. Your application appears to have low CPU usage, so it looks fast, but your latency is terrible. We traced mysterious P99 latency spikes to 10 to 15% CPU steal time. The thresholds that matter: steal time above 5% consistently is concerning. Above 10%, you're losing significant performance. Here's the critical insight. The fix isn't optimizing your code, it's choosing different instance types or using reserved capacity to guarantee you actually get the physical CPU you're paying for. Use mpstat-p all 110 and look at the percent steal column. If you see consistent steal above 5%, your instance is oversold or you need to upgrade. 9. Part 2. Memory troubleshooting. Now let's tackle the most misunderstood resource: memory. Linux memory management is radically different from Windows or other. So how do you know if you actually have memory pressure? What are the real indicators? There are 3 signals to watch for. First, page scanning activity. This is the kernel desperately searching for memory to reclaim. Second, swap activity, actual swapping in and out. Third, available memory below 10% of total. Here are the commands. Use vmstat1 and watch the SI and SO columns. These show swap in and swap out. If these are consistently above 0, you have pressure. Use SAR-B160 to see page scanning rates. The metrics are PG_scan-K per second and PG_scan-D per second. High scanning means the kernel is struggling to find memory. Let me give you a real case. We had a service using 19.5 gigabytes of 20 gigabytes of RAM. Engineers wanted to upgrade to 32 gigabytes. Seemed reasonable, right? But we ran vmstat and saw 0 swap activity. Page scanning was minimal. Available memory was 400 megabytes. The service ran for months without any issues. The kernel was just efficiently using all available memory for cache. Most reported memory leaks are actually legitimate application growth, page cache behavior, or memory bloat, not leaks. True memory leaks show as unbounded RSS growth over time, regardless of workload. 12. RSS versus VSZ and the OM killer. When someone tells me their process is using 10 gigabytes of memory, I always ask, RSS or VSZ? VSZ is virtual size, the total virtual memory allocated. This is mostly meaningless. A process can have 50 gigabytes of VSZ but only use 2 gigabytes physically. RSS is resident set size, the physical memory actually in RAM. That's what matters. Modern applications pre-allocate huge address spaces, but only physically use what they need. Don't panic about high VSZ numbers. Now the OM killer. When Linux runs out of memory and swap, the out-of-memory killer terminates processes. But its algorithm is counterintuitive. The OM killer calculates a badness score for each process. High memory users get high scores. Recently started processes get high scores. Processes with many threads get high scores. The result? The OM killer often kills your most important process, your database, your cache, because it's using the most memory doing exactly what you told it to do. Meanwhile, your tiny monitoring agent survives. The command to check this, cat/proc/star/OOM score. See which processes have high scores. Protection. Echo -1000 into /proc/pid/OOM score-AJ. This makes the process immune to the OM killer. Set this for critical services. Check OM events with dmessage, pipe, grep-I, kill. 13. Part 3, I/O troubleshooting. Now let's tackle the third major resource, I/O. This is where most engineers get stuck, because the I/O stack has so many layers, and the bottleneck can be at any of them. Let's learn to find the real problem. 14. I/O wait time, the misconception. I/O wait is the most misunderstood metric in Linux troubleshooting. When someone says, we have 40% I/O wait, so our disks are slow, I immediately know they don't understand what they're measuring. I/O wait is not disk speed. I/O wait is CPU idle time while at least one process is blocked waiting for I/O. That's a huge distinction. There are two patterns you need to recognize. First, high I/O wait with low disk utilization. This means your application is the bottleneck, doing synchronous, single-threaded I/O. The disk can handle more work, but your application isn't giving it enough concurrent requests. Second, high I/O wait with high disk utilization. This means the disk is actually saturated. Let me give you a real case. We had a service with 35% I/O wait. Everyone assumed slow disks. But I/O stats showed disk utilization was only 20%. What was happening? The application was reading files sequentially in a single thread. We parallelized the reads across 4 threads, and suddenly I/O wait dropped to 8%, while throughput tripled. Same disk, completely different performance. The command is iostat-xz110. Compare the %util column with I/O wait from top. High I/O wait with low %util means fix your application architecture. High I/O wait with high %util means your disk is actually the bottleneck. 15. IOPS versus throughput. Storage has two primary limitations, IOPS and throughput. Most engineers confuse these, and it leads to wrong optimizations. IOPS stands for input-output operations per second. This measures small, random reads and writes, typically 4 kilobyte operations. Throughput measures megabytes per second for sequential operations. Here's the key insight. Most applications hit IOPS limits before throughput limits. Let me give you the numbers. A modern SSD can do 300,000 IOPS, but only 3 gigabytes per second throughput. A spinning disk can provide 150 megabytes per second throughput, but only 100 to 200 IOPS. Pattern recognition is critical here. Small random reads and writes are IOPS bound. This is databases, indexes, metadata operations. Large sequential operations are throughput bound. This is ETL jobs, batch loads, video processing. Real optimization example. We redesigned a reporting system to batch many small reads into fewer large reads. This reduced IOPS by 80% while maintaining the same total throughput. The disk could suddenly handle much more work. The command is iostat-xz1. Look at R per second and W per second for IOPS. Look at R megabytes per second and W megabytes per second for throughput. Know which one is your bottleneck before you optimize. 16. The I/O stack. Where's the real bottleneck? An I/O operation travels through many layers before it reaches the disk. Each layer can be the bottleneck. From the top, your application makes a write or read call. This goes to the VFS, the virtual file system. Then to the specific file system, like ext4 or XFS. Then through the page cache or direct I/O path. Then to the block layer. Then through the I/O scheduler. Finally to the device driver and hardware. Here's what most engineers miss. Each layer has different bottleneck patterns. For example, we've seen cases where disk utilization was only 40%, but the file system was saturated due to metadata operations. Creating and deleting thousands of small files was bottlenecking on inode operations, not data I/O. Another common pattern in distributed systems, network I/O masquerading as disk I/O. You see high I/O weight, you assume slow disks. But the actual bottleneck is network latency or packet loss on network-mounted storage like NFS or Ceph. Real story. We spent days